let's start with a quick revision of what we already have learned about dilations and translations of exponential curves. So we can dilate or stretch a curve horizontally or vertically, and we do this by just dividing x or y by a scale factor. We call this scale factor sometimes a or n or something like that. And if the scale factor is -1, that's a dilation that's also known as a reflection because it flips it or flops it upside down. We can also move curves left or right or up or down by just replacing x by x plus or minus something, or replacing y with y plus or minus something. Now let's look at our basic exponential curve. It's got an asymptote on the x-axis. It comes up sharply on this side. It always goes through 1. And you can label one other point to give it some scale. So I've labelled the point 1e. And just by subbing 1 in for x, I can see that y would equal e to the power of 1, which is just e. Now, I'm going to start by graphing this horizontal dilation. You can see that instead of e to the power of x, I have e to the power of x divided by 2. So clearly my scale factor is 2. What does that mean? It means that every point on the original curve is now going to be twice as far away from the y-axis as it was before. So I can take a point like this, have a look at how far it was from the y-axis, and double it. It'll be out here somewhere. A point like this, you can take any point and double its distance from the y-axis. So you can quickly and easily see that it's going to be a much sort of slopier, a lower down slope, sort of a fatter curve if you like. It's still going to go through 1 because that can't move from the axis that it's on, and it'll come down like this. So we've stretched it, and let's label this y equals e to the power of x over 2. Now, one like this actually looks a little bit trickier. Let's do green pen for this one. Y equals e to the power of 2x. What's my scale factor here? Well, this is a trick one because what we've actually got here is y equals e to the power of x divided by a half. But it's in disguise looking nice and simple like this, 2x. Now, how does this work? How does it work? Well, you'll remember that if we divide something by a half, that's the same as multiplying it by 2. So even though it's been written like this, we need to think it through as this way to see what the scale factor is. And the scale factor here is a half. That means every point is now going to get half the distance that it was from the y-axis. So we're going to halve all of these distances, and it's going to make this curve quite skinny here, but it'll come down lower down here because we've halved all of those distances. So this one is, let's label it over here, y equals e to the power of 2x. And that's a little bit deceptive. The scale factor is actually a half. Now for some vertical dilations. Now it'd be nice to think that we're replacing the y with something, but often the question that we're given will have y sitting all by itself on the left-hand side of the equation and some other stuff that looks a bit messy on the right. So it's up to us to work out what that scale factor would have been, and we can do it by just rearranging the formula a little bit. So starting with this purple one here, if I was to rearrange it and write it this way, now it's easy to see that it's just like our original graph, except the y has been replaced with y divided by 2. That means that 2 is the scale factor. So we're stretching this way and we're making all the points twice as far now away from the x-axis so that they're changing in y value. So take any known point, we can start with this one. Instead of being 1 unit away from the x-axis, it's now going to be 2. This point here, instead of being e, will now be 2e. So that will be 2e there. So we're going to get the graph stretching upwards like this. And all of these points are going to get twice as tall as well. So it's going to come down like that. And we can label this purple one y equals 2e to the x. And we can see that what it really is a vertical stretching with a factor of 2. For the green one, it's written this way, but if I rearrange it, I could multiply both sides by 2 and see that what I've actually got is this. Now, does this help me? Does it give me y divided by something? Well, no, we've just seen that this is the same as y divided by a half, because dividing by half is the same as multiplying by 2. So this is a bit of a trick one. And what we've actually got here is this arrangement, where we've stretched it vertically, but by a half. That means we've actually shrunk it vertically. So to draw this one, take each point and see how far away it is from the x-axis and then halve it. So this point will come down to here. Instead of e, this will be half of an e, and so on. This one's going to come down more this. And we can label this one as that, y equals e to the power of x divided by 2. Now let's have a go at moving the curve left or right. Now to do that, x needs to have been replaced with x plus or minus something. And remember, plus moves us left and minus moves us right. So this example, y is equal to e to the power of x plus 2, that moves our original curve left 2 units. So take your known point here and move it across 2 units. So instead of being 0, 1, it will be minus 2, 1. That gives us a new known point. Our asymptote is still going to be in the exact same place down here on the x-axis. And the whole curve is moving across, so you can pretty much go ahead and rough in your basic shape here, something like that, and label it y is equal to e to the power of x plus 2. Now we need to find this intercept here. How do you do it? Well, you let x equal 0, plug it in here, and we'll have y is equal to e to the power of 2. So that's e squared, and I can just label that as the point e squared. That one's done. All right, this example here in purple, we're now moving vertically, and we're shifting it up or down. Now there's 2 ways to remember it. One way is, you know this is a function, so if it has a plus 2 tacked onto the end, like an afterthought, rather than involved directly with the x, then it's going to shift the curve up. You can also rewrite it if you want to into this form so that you can more clearly see that y is the thing that's been replaced by y minus 2, and that also shifts it up 2 units. Now to shift it, move your asymptote first. That lifts everything up. So instead of being down here on the x-axis, it's going to be up 2 units. So we can dot it in like that. Ruler would have been nice, but that's okay. And then our known point is also going to come up 2, so it's going to come up 2 to about 3 here. Well, to exactly 3 actually. And then we can go ahead and rough in, well, that's not a great drawing, our new curve and label it y is equal to e to the power of x with a big plus 2 at the end. Now it hasn't got any scale at this point, we need an extra point to give it some scale. So this original point would do, it was the point 1, comma, e. If we've lifted it up 2 units, it will be 1, but instead of being e, it will be e plus 2. So that knowledge of the original curve that I have there in black is really helpful when it comes to moving things up or across, or dilating them, stretching them, or compressing them either way. Now, what we haven't thought about so far is a special quality that these exponential curves have. Well, we've thought about this, but we haven't thought about what it means in terms of dilating and translating. Now, we know that when we differentiate e to the power of x, we get e to the power of x. And what that means is that for this curve, its height and its gradient are always exactly the same. So it has a real proportionality that's important. Now what that means is that when we dilate or stretch this graph one way or the other, it's almost like we're zooming into a different section of the curve. And that's very similar to actually sliding it left or right. Now this doesn't happen with any other curves. It's a special feature of exponential curves that any dilation can actually be expressed also as a translation, and any translation can actually be expressed also as a dilation.